Yeah, thank you very much. So yes, so the idea is so this is joint work with Marco Paviotti and Michael Vollmer, both at the University of Kent, and I will explain a bit what's the idea behind this. So the keyword here is hylomorphisms. For those who never heard about that before, this is essentially, you can think of this as the most general recursion scheme. So recursion schemes are high-level patterns of recursion. They are nice to use because they free the programmer from developing their own recursive function, and instead they can rely on some high-level combinators to structure the recursion, and that in turn gives them some nice reasoning principles. And in fact, you can use the laws that are associated with these patterns of recursion to do program transformations and optimizations. In particular, I'm going to talk about about fusion and how you can fuse multiple recursive traversals together. Many of you probably heard about the optimization deforestation that has been proposed for example, for the Glasgow Haskell compiler, and there are many alternative proposals for this, including a very famous one, is the fold R build approach. And so encoding hylomorphisms in rock, which is this very general recursion scheme, essentially has a bunch of benefits. In particular, if you structure your recursion using this, you reduce the burden of the determination productivity proofs, essentially because you can develop your algorithm modularly. You can build it in terms of smaller pieces, and you can do the relevant proofs to the relevant components, and then use the laws to fuse them into a single recursive function. And you can use the hylomorphism laws to do this type of calculations and optimizations using regular rewrite rules in rock. And finally, the final benefit is that these implementations that you can develop using this can be extracted to code that you can run. Okay, so with that being said, so I'm going to start with a very brief introduction to and lightweight introduction to hylomorphisms. And in particular, I'm going to start talking about folds as initial algebras. I'm sure the majority of you are familiar with this, but just as a small recap. So this is the usual fold definition in Haskell, so for lists. So essentially, you have like the base case and the inductive step, and for the empty list, you just return the base case, and then you apply your function g to the head of the list, followed by the folding the tail of the list. So this is the usual case. So another way in which you can view these folds is as initial algebras, and I will again talk in a very lightweight way about this. So an algebra, so one way to describe an algebra is in terms of a carrier set and a set of operations which are defined by a function. In particular, in this case, this would be this function fx to x, defined by some functor. And the idea is that the initial algebra, so we can define the initial algebra as the least fixed point of a functor. So this would be a definition in Haskell. And in particular, the idea is that so this is the initial algebra essentially because there's a unique map that goes from this initial algebra to any other algebra. And this is witnessed by what is known as the catamorphism, which is defined here in Haskell. In particular, what you do is you unwrap your inductive data type, and then you apply the algebra and you compose the algebra with the recursive application of the catamorphism to the sub-elements in your algebra. And oops, sorry, I jumped ahead too much. Right. So this is the F algebra. This is the initial F algebra, and the catamorphism is the unique map that goes from this initial algebra to any other algebra, as I said. And now we can recover the definition of fold R with a definition of lists that is the least fixed point of this functor, this functor that has two cases, nil and cons. And this is the same diagram, but instantiated through this definition. Right. So now let's move on to hylomorphism. So we can generalize this. And we can essentially you can view this in this diagram. For example, what we're saying is that the catamorphism is the unique arrow that makes this diagram commute. But we can shift the direction of this arrow, and we can take the co-algebra, so the observations that we can make on the syntactic data type, and we can go one level up, then mapping the recursive call, and then going all the way down. And this is essentially how we generalize it into divide and conquer recursion. And you can view this as so we have now a co-algebra that for the purposes of our talk just splits our input into some structure F. Then we map the recursive call, and then we do the conquer part with the algebra. And and this is just an instantiation of this. As I said, this is just a matter of reversing this arrow, and now you can view a fold as a hylomorphism, as a divide and conquer. And this is just one example of recursion scheme that can be represented as a hylomorphism. There are a wide range of recursion schemes. In fact, every single recursion scheme can be seen as a hylomorphism, or in more precisely as a conjugate hylomorphism. And in our paper, we show examples, for example, of the finite memo table. So we use a recursion scheme called dynamorphism, and we show an example. We have further examples of these. But yeah, so through these adjunctions, you can essentially take any recursion scheme and represent it as a hylomorphism. So yeah, right. So what are the challenges for encoding these hylomorphisms in ROC? Well, the first one is we want to avoid axioms, and we want to accept program calculation in a way that closely resembles what you would find in a pen and paper proof. We also want to be able to extract idiomatic code from this encoding of hylomorphisms, and we need to deal with terminations and co-fixed points of functors. So all of these together are the main challenges. And our solutions are to avoid axioms. We essentially since we need to reason a lot about the qualities of functions, and I will talk a bit about our use of containers later. So we essentially build some machinery to deal with the setoid hell, which everybody here, I'm sure, are familiar with. And we restrict to using decidable predicates. I will talk also a small bit about this later. Also, to help with extracting code, we avoid the use of type families and index types. And okay, this is a bit surprising for using a dependency type language, but that's unfortunately what we have to do if we want to extract code that does not contain unsafe casts and things like this. And our solution for dealing with termination at the co-fixed points of functors is the use of containers and recursive coalgebras. So just a small bits about containers. So just for those that are not familiar with this, so a container, you can see this as a pair with a type of shapes and a family of positions indexed by this shape. So this is the standard definition. And a container extension is a functor that is defined essentially as this existential type where we have one shape and then a function that goes from the positions in that shape to the type x that is the argument to your functor. And the functorial action is simply defined by post-composition. So it's not very surprising given this definition. Okay, so just as a small example, if we want to consider these functors, which is 1 plus x times x, with the argument being x, So the shapes that would define this container would be 1 plus 1, essentially because we have two cases, so we have two shapes. Since we have no occurrences of X on the left, then this has 0 valid positions. And since we have two positions on the right shape, we have essentially the sum type of, well, either in L or in R. And here we have a couple of examples of objects of this type that are isomorphic to the corresponding f of n. Right. So how do we mechanize containers in rock so that we get clean extraction? Because if we do the direct encoding of this, we have lots of problems for our set of challenges. In particular, for example, we would need to reason about heterogeneous equalities of positions, which would force us to add some axioms. And furthermore, if you try extracting code from these, and we have in our initial attempt at this problem, then you end up producing code that looks like a mess of unsafe coercions and so on. So what do we do? So we restrict, so we have a slightly funky definition of containers that may raise an eyebrow here, but in particular, well, first of all, since we use setoids, we write this squiggly arrow to denote proper morphisms. And this is essentially what we use, where A and B and setoids, and we will use a different symbol to denote the setoid equalities. So this avoids the functional extensionality. And now containers are defined by 3 components. Shapes, a type of all possible positions, not just the positions in that shape, and a decidable predicate that tells you when a position is valid in a shape, which avoids the need to add axioms to deal with these heterogeneous equalities of positions. And now, our container extensions are defined by recovering our family of positions by essentially adding thinking about our family of positions as a predicate subtype of the positions, where we simply check the case where the position is valid in a shape when this function returns true. So what does this mean? Well, this means that the extraction will treat this function equivalent as the type of positions to X, so there will be no unsafe coercions, and also we can discard the second component when reasoning about the quality of positions. Right. So with this machinery in place, so we can start defining least and greatest fixed points of container extensions in this particular case. Oh, by the way, with this definition, I should mention that in our mechanization we have represented polynomial functors. So for our purposes, this is sufficient, but I understand that there will be some cases where the use of this definition may not be as expressive as one that is directly encoding positions as families of indexed by a shape. But anyway, right. So with these definitions, this becomes rather straightforward. So essentially, we can take the least and greatest fixed points of these containers, and then we can define our kata and anamorphisms. In a standard way that satisfy the usual universal properties. In particular, so if you focus on the katamorphism, so this essentially is the proof that the diagram that I showed at the beginning for the false commute. Okay, and it's important also to note that we have essentially this higher order treatment of all these functions because because we want to be able to treat those as data. So I will talk about one limitation at the end and how we can address this by being able to, for example, produce an anamorphism with a recursive function. Okay, now the hylomorphism equation, what you saw, like F composed with, this algebra composed with F map F composed with the coalgebra. So this cannot be encoded directly in rock, of course, but it can if we restrict to the so-called recursive coalgebras. And there's essentially a number of equivalent definitions of recursive coalgebras. And in particular, so in our formalization, what we do is we define this inductive predicate that states that C can only be applied recursively on some input X a finite amount of times. And but there's another alternative definition that we also have in our formalization that is, well, a well-founded coalgebra for some well-founded relation R is one such that the contents of the result of applying the coalgebra are related to the input. And those two definitions are equivalent. This is also shown in this paper. But we build our definitions on top of the first one, and in particular, the determination proofs in some cases are easier to do with the definition one. For example, if you have a structural recursion, and in some cases it's easier to do with two. For example, if you need to do some complex reasoning about some size of your input, then it may be better suited to use a well-founded coalgebra. Now, and this is, by the way, I want to bring the point that I said at the beginning. So the fact that you have this means that you have a more modular treatment of determination proofs. Now you need to look only at the coalgebra. You don't need to look at your whole recursive function. And you can imagine having a library of recursive coalgebras that you can reuse and compose and build into further recursive coalgebras. Okay. So now, the core definition for recursive hylomorphisms is the following. So essentially, with this, equipped with this definition or this inductive proposition that says that the coalgebra terminates, our hylomorphism is simply an encoding of the hylomorphism equation, but recursive on the proof that the coalgebra terminates for some input X. And in particular, if you notice in this definition, so we start by applying the coalgebra, and then we apply the algebra to the F map. This is a bit harder to see, but not too much. So this is, you can see that how this is essentially the F map of the recursive call inside the container, because this is essentially applying F to the contents of the result of applying your coalgebra. And we have this inversion that we can use to pass as an argument to the fixed point for the recursive calls. Right. And with this, essentially, we can build hylomorphisms as a wrapper on top of this, where we have our algebra, our recursive coalgebra, and this gives us an arbitrary function from A to B. And with any algebra and coalgebra, I'm missing here, by the way, determination. There's a typo here. This should state that that this coalgebra is recursive. But we have that the hylomorphism is the unique solution to the hylomorphism equation. Right. So the standard laws of hylomorphisms are straightforward consequences of this uniqueness property of the recursive hylomorphism. In particular, what we can do is we can prove that we can fuse a function composed to a hylomorphism into a single recursive traversal on the left and on the right. And as a consequence of either of those, it doesn't really matter. We can prove that we can fuse two hylomorphisms into a single one. So we can use these to do optimizations. Right. And just to mention, thanks to our use of setoids and the machinery that we built, the proofs that we do to show these laws are exactly as what you would expect in independent paper proofs. In particular, for example, for the hylofusion L that I show on the top, what we have is that if this diagram commutes, that means if H composed with A is the same as B composed with F map H, and the right-hand side is given by the Hylo equation on A and C, that tells us that H composed with a hylomorphism with an algebra A and coalgebra C must be equal because the hylomorphism with the algebra B and the coalgebra C is the unique arrow that makes the outer square commute. So that means that we can fuse H into the hylomorphism. Okay. Yeah. I'm going to show you just the simplest example of extraction. As I said in the paper, we have also mechanized shortcut deforestation as described by Takano and Meyer. But here, this is just to illustrate how our definitions produce code that closely resembles what you would write. There are some limitations that I will talk a bit about, but yeah. In particular, let's look at the standard definition of a quicksort. And here, to define our algebra is just the concatenation of our list with the pivot and the rest of the list. Well, of course, in the base case, you just return nil. And we have a split function, which is our coalgebra that takes a list and produces a leaf, or partitions the list in two and produces a node, one node of a container. This is a container whose fixed point would produce a tree. Right. By using our approach, we can extract this. I can show you a demo of the different things that you can do later after the talk if you're interested, because we can play with this a bit more. And what if we want now to fuse another recursive traversal? For example, we want now to multiply all of the elements of our hylomorphism by 2. Well, we can just apply hylofusion here. I'm omitting a proof, which is the precondition for hylofusion, but this is just using more of the laws of hylomorphisms for fusion, and also some properties of natural transformations, which are required to model this mapping of times 2 into a list. And this, if we use extraction, this produces exactly what we would expect, which is the same definition as hylomorphism, but the pivot is now multiplied by 2. Now, one thing that I wanted to mention is that, unfortunately, we were completely unable to make rock inline this definition, which is a bit unfortunate, but this is nothing that a simple compiler pass couldn't do, and in particular, we were even looking into ways of adding manual inline annotations to force the inlining of these functions. Right. There are further details in the paper. I glossed over lots of things here. In particular, we also deal with coalgebras and anamorphisms. I showed them in just one slide, but you have more papers there. As I mentioned, we mechanized the shortcut deforestation optimization in Takano and Meyer's paper, and also we show an example of dynamorphisms as an example of a more advanced recursion scheme that can be encoded in this approach. I also didn't talk about, because one concern that you may have is, okay, I have now my definition as a hylomorphism, but how easy it is for me to prove the properties of our functions? Well, it's comparable to any other approaches for encoding non-structural recursion in rock, and with the added benefit that you can again do your proofs modularly. If you can fuse a series of function compositions into a single definition, then what you can do is you can prove your property piecewise for each of your pieces, and then you can use program calculation, and you know that the result of your fused program will satisfy the same property as the input, because you know that they are extensionally equal. Right. And this is just a wrap up. So we have this modular specification of functions using hylomorphisms and the hylomorphism laws. And we did it in a way that allows idiomatic code extraction. Just to mention, this required lots of iterations because of the weird interactions with code extraction. I should say that it's something that was not finding the right definitions was not definitely not straightforward. But there are limitations I didn't mention. I just wanted to talk a bit about some. In particular, for example, with conversations with Michael, one of the co-authors of the paper, who worked in array languages, or languages for array computations. So he was rightfully mentioning that the container representation of a list is really what people know in array languages as a pool array. And actually, you can use hylomorphisms to do divide and conquer computations that deal with these pool arrays, but we are missing the push arrays. So probably by using some monad with some distributive law, we can encode also push arrays, but this is something that we have not explored, and this is actually something that would be interesting to look into. Dealing with setoids and inequalities, we provide a series of tactics and machinery to help avoid the majority of them. But for example, in the case of the dynamorphisms, our machinery did not do those proofs automatically for us. We needed to do, if you go into the code, we needed to add lots of things there. So we need to deal much better with that. And the other big limitation that I didn't mention is that we do not deal with co-inductive programs. We only deal with inductive programs. And we are still looking into this. I had a small conversation with Robert yesterday about this, where he suggested the use of guarded recursion for in ROC, but we would lose the ability to extract nice code. So I'm not entirely sure what the solution there is. And that's essentially it. So thank you very much.